Hello, grade 11 chemistry students. Today we are going to learn about the orientation effects of different substituents. This theory is explaining about the orientation effect. To explain why the electron donating substituent are 2.4 directing and why electron withdrawing groups are 3 position directing, we need to return to the electron distribution in carbocation intermediate mentioned in previous pages about the benzene. Okay, in bromination of benzene. Okay, this is only bromine, only one type of functional group substitute hydrogen in benzene. The intermediate can be represented as follows. Okay, so this electron donating the diff covalent bond with the bromine electrophile, and then there is a partial positive. The double bond open that binds with that make covalent bond with Br, and the other one with the hydrogen. Okay, let's see. The positive charge, that is the electron deficiency. Positive charge means less of electron, is due to only 4 electrons being spread over 5 carbon atoms. So we do not consider this carbon atom because this carbon atom make covalent bond with hydrogen, bromine, carbon and carbon. But the deficient is here, this one. Okay, but the positive charge is not evenly spaced. So the positive charge is not evenly spaced. What does it mean? It means the distance from here to here is not evenly spaced. There is an overlap pi bonding system. There is an overlap of pi bonding system. But in the other one, in here, there is no overlap of pi bonding system. It is mainly on carbon atom 2, 4 and 6. So carbon atom 2, 4 and 6. And then electron donating groups at this position will therefore more effective at stabilizing the intermediate, spreading out its charge than if the electron donating group were in position 3 or 5, one carbon removed from the positive charge. In here, this is different condition. What does it mean different condition? In the top one, only one type of functional group, and it is bromine. But in here, there is a methyl, and there is this one, bromine. So let's, as you can see here, there is a blue arrow. Blue arrow, it means there is a positive inductive effect. This one from the CH3 give positive inductive effect to the positive. So in here, if the methyl group is situated in 2 or 4 relative to the bromine atom, the intermediate is much more stable compared to the intermediate in the substitution of benzene. This theory is consistent with the previous one. The previous one on page 436. Let's see the structure of benzene when there is one more functional group added. So here CH3 here in the position of this one, and then this one in the position of 2. So there is a high possibility. So 2 and 4. Okay, let's go back to the theory. Now this one, and then this is consistent. So if there is in here, there is position of 2 and position of 4. See here, position 2, this one position 4. Okay, if the methyl group is situated in the third position relative to bromine atom, the intermediate is little more stable compared to the intermediate substitution in benzene. It is little more stable, but it is not stable. This is in here position 2 and 4 much more stable. So we have to know that whether there is an electron donating group. This is consistent also with the previous theory. This one electron, this one, this one, position 2 and 4 directing substituents. CH3, because there is a positive inductive effect, although it doesn't have lone pair like OH, like O in the OH, and also like N in NH2, but there is a positive inductive effect in CH3. Okay, next let's continue to this one. Addition reaction of the benzene ring. We know that benzene will not undergo addition reaction, but it will undergo electrophilic substitution. However, under some condition, it can be forced. So highlight, it can be forced, meaning under very harsh condition. And then ethene adds on hydrogen over nickel catalyst readily at room temperature and slight pressure. But for benzene, in order for the hydrogen to be added into the benzene, from benzene into cyclohexane, it requires nickel 200 degrees Celsius, high temperature, and also high pressure. Okay, so requires harsh condition. And then now substitution in the side chain. Methyl benzene and other alkene benzenes very readily undergo radical substitution. Radical in here means free radical substitution, or called as homolytic fission, with chlorine, bromine, or with other group 7 elements in the presence of UV light. But if there is no UV light, this reaction will never undergo. So we need to keep in our mind that there are two reactions of methyl benzene with chlorine. If number one, if chlorine reacts with methyl benzenes in the presence of aluminum chloride, then the chlorine will be substituted into the benzene ring. Second reaction, when chlorine reacts with methyl benzene in the presence of UV light or boiling, then the chlorine will substitute hydrogen of the methyl group. So it will become chloromethyl benzene. Okay, this one different reaction, and then in ethyl benzene, hydrogen atom on the carbon atom adjacent to the benzene ring are substituted much more readily than the 3 hydrogens on the other carbon. So the following reactions gives a good yield of the product. Why is the Cl not located over here, but the Cl is located over here? The hydrogen atom adjacent to the benzene substituted more readily than the 3 hydrogen on the other carbon, because there is a positive inductive effect in this one. There is positive inductive effect that push the electron here. Okay, now let's continue to the oxidation of the side chain. When alkyl benzenes are treated with hot alkaline potassium manganate, please highlight the catalyst is alkaline condition and also potassium manganate, and then the condition is hot. Oxidation of the whole side chain occurs, leaving carbon atom closest to the ring as a carboxylate and carboxylate or carboxylic acid group. And then, so this one, alkyl benzene, this is ethyl benzene. When reacts with potassium manganate in the alkaline in hot condition, it will oxidize this one, or we can call as hydrolyze this one. This one will be cut, so the CH become alone. CH3 will be separated and then become salt. This become the salt, and then in the presence of acid, this benzene, which was the salt, and then become benzoic acid. Similarly, if there are two alkyl attached to the benzene in the presence of potassium manganate heated with alkaline, this one, both of the alkyl group will be substituted, and then in the presence of acid, this become dibenzoic acid. Okay, so like this one, 3 carbon ABC with the formula C9H12 will oxidize hot potassium manganate. Hydrocarbon A give benzoic acid, hydrocarbon B give 1.2 benzene 1.2 dioic acid, and this one will form 1,2,4 trioic acid. The structure, this is the possible structure. Okay, and then next time I'm going to explain about halogenoarenes, the reactions of the halogenoarenes.